Welcome back. In this video, we're going to continue looking at some more advanced algebraic techniques. So this video is about how to solve systems of linear equations, and we're going to be introducing a third variable. So we're going to have a system of equations with 3 equations and 3 variables, and we're going to go through techniques on how we can solve those and all the different cases, because there's 3 different cases. Let's just start off with a really straightforward one. So if you ever need to use a calculator or if you're allowed to use a calculator to solve these, it's quite simple. So that's what we're going to do with example 2.6. So if we pull up the calculator, what we want to do is go into algebra, solve system of linear equations, 3 variables, x, y, z. And then let's type in our equations. So we have 2x plus 4z equals y take 9, so on and so forth. What's that? Minus 3z minus 15 equals 0, and then equals 5 take z. Quick double check. Yep, pretty sure that's all good. Solve. Okay, there's our solution. So if you can use a calculator, this is pretty much nothing required. And alright, now let's get to the fun stuff. Okay, so number your equations, your starting equations 1, 2, 3. Now you can perform algebra with any of these, and you can create new equations in order to get to what you want, because at the end of the day we want a value for x, y, and z, right? So we need to start off by trying to get a step closer. So essentially what I want to do here is perform some operations to these equations to try to eliminate one of these variables. And what we want are two new equations that has either x, y, or z eliminated. Alright, now at first glance I think it's going to be easiest to eliminate the z. So if I do equation 2 plus equation 3, that gives me, now just for the sake of the video, I'm just going to work out I'll show the new equations, but I'll do it mentally just to save time. And you can always go back and try to double check yourself. So 4x plus 6y equals 4, and this is where you can continue to simplify it. So you can divide everything by 2. Alright, and then I'm going to call this equation 4. Alright, so that's one new equation that's got the z eliminated. Now I need another one. So I'm going to try to find another combination of equations that's going to help me eliminate the z. So if I do equation 1, take away 3 times equation 3, that will also eliminate the z. So that will give me negative 7x take 7y equals negative 14. So that means x plus y equals, divide by negative 7, right? So equals 2. Call this equation 5. Okay, so now what we're going to do is we're going to keep the first equation there, because we're going to use that later. You can always do this, just leave that first equation there anytime you try to solve this. And I'm going to replace equation 2 and 3 with 4 and 5. So I get 2x plus 3y equals 2, and x plus y equals 2. Alright, and now see how I have 2 equations now, 4 and 5, and 2 variables. I can now eliminate one more. So now if I can do equation 4 take 2 times equation 5, alright, that will eliminate the x. You can eliminate whatever you want. I'm just eliminating the x here. So I'll get y equals -2. That works. And I'm going to call this equation 6. So keep equation 1 there. Now, since I only have one new equation, I can just choose to replace one of these equations. I don't need to come up with another one. Because the point is, see how I've isolated a single variable for y? Right now we can basically use the two equations above that to try to solve for x and z. So since y equals 2, well, that means let's just do some working. So sub into equation 5. So 2x plus 3 times -2 should equal 2. So that means x should equal, well, 2 plus 6 is 8. 8 divided by 2 is 4, so x is equal to 4. Now let's use our two solutions for x and y to sub in into equation 1, which is right there. That's why we kept it there, to find the value of z. So 2 times 4 minus -2 plus 3z equals 13. Alright, so that means 3z will equal 5. No. Yeah, 5 minus, sorry, mind blank. 3z is going to be equal to 3, z is going to be equal to 1. So, therefore, solution x is 4, y is -2, z is 1. So, this system here, the solution to this system is called a unique solution because we have unique values for x, y, and z. Right, that's one case. Now, in the next example, we're going to look at another case where this system of equations has infinitely many solutions. All right, and then we'll go ahead and try this. So let's paste this over here. And let's start with that. So let's number our equations. So first of all, we need to just try to get some isolated variables, right? So let's just do what we did before. I like to set it out like this. I think it's neat for me, for my brain. So you can set it out similar if you want. All right, so after we solve it, then we're going to find the general solution. So let's go ahead and go through this one. Okay, so y would be really easy to eliminate to start off if we just do equation 2 plus equation 3. So we get 8x, take 4z equals plus equals 12. Our common factor of 4, so we'll get 2x, take z equals 3. Call this equation 4. And we want another combination that will eliminate the y for us. So if we do something like equation 1 take 3 times equation 2, that'll do. So that will give us -4x, y's gone, plus 2z equals, so 6 minus 3 times 4 is -6. And if we divide by -2, we get 2x minus z equals 3, which happens to be the same as equation 4. But we've used a different combination of equations to get here, so this is actually equation 5, even though it's the exact same thing, right? So this is when you know your system has, well, the sign that your system has infinitely many solutions. So let's go and rewrite this as a system. So keep the first equation there. Write equation 4. So replace equation 2 with equation 4, just like in the previous example. And then replace equation 3 with equation 5. Alright, now if we do equation 4 take away equation 5, we get 0 equals 0. Alright, which means that there's infinitely many solutions in the system of linear equations. So we can proceed to this final step here. Alright, 2x take z equals 3. 0 equals 0, so that's 1. It's equation 4 or 5, whichever one you want. Now call 0 equals 0 equation 6. Alright, so if you ever get 0 equals 0, that means your system has infinitely many solutions. Alright, so that's A, done. The system has infinitely many solutions as 0 equals 0. Now, find the general solution. So what we do is we let z equal another variable, so we'll use lambda. Alright, so that means z can be whatever number, okay? So now if we sub this into equation 4, whoops, I keep doing that, I gotta stop. If we sub this into equation 4, then we have 2x minus lambda equals 3. So basically we just want an expression in terms of lambda for x, y, and z. Alright, so that means x equals lambda plus 3 on 2. Alright, and now we have z and x, we can find y. So if we use equation 1, and sub our expressions in, so 2x plus 3y plus 8z equals 6. Let's solve for y. So the 2's will cancel out. 8 lambda equals 6. So if we get 3y by itself, we'll get 6 minus 3, which is 3, and then minus 9 lambda. So that means divide everything by 3. Y equals 1 minus 3 lambda. Okay, so that just means that we have expressions for all x, y, and z, and we have lambda, which can be anything. So therefore, we have infinitely many solutions. So the general solution is x equals lambda plus 3 on 2, y equals 1 minus 3 lambda, and z equals lambda. Alright, so that's case number 2. We got one more case to consider, and that's when the system is what we call inconsistent and it has no solutions. Alright, so both of the examples we just did, if it has a unique solution or if it has infinitely many solutions, they're called, the system is consistent. Alright, now let's have a look at this final example here. Whew, doing well. Okay, so they've already been numbered for us, which is great. So let's go ahead and try to do some working out. So let's eliminate x to start with. So we want two equations with x gone. So if I do equation 1 minus equation 2, actually let's do 2 minus 1, keep everything positive. So we get y plus 2z equals negative 6, but the variables are positive is what I meant. Alright, and then let's find another combination. So if we do equation 3 minus 2 times equation 1, we'll get we'll eliminate x as well. So what's that? 3 minus 2 is 1y, and then 4 minus 2 is 2z, and then 9 take 20 is negative 11. Alright, so here's our equation 4, and here's our equation 5. Alright, let's go on to the next step. So x plus y plus z equals 10, equation 1. So replace equation 2 with one of the new ones. So we'll do equation 4, and then replace equation 3 with one of the new ones. And you can probably already see why there's a third case. Alright, so now if we do equation 4 minus equation 5, what do we get? 0 equals negative 6 take 11, 0 equals take negative 11. Just checking my math. 2 minus 1, yep. 3 minus, we get 0 equals 5, which is not true. So therefore, there are no solutions for the system that will, there are just no solutions for the system. So what we say is, alright, let's just finish setting this out. So y plus 2z equals negative 6, and then 0 equals 5. So call this equation 6. Alright, so therefore there are, and this, as soon as you get to something nonsensical like this, that just means you have no solutions. So there are no solutions to this system. And we're done. Alright, so something new there for you. Alright, quite lengthy. Alright, but it does get repetitive, and after a bit of practice, you'll be totally fine. Alright, thanks for watching, and I'll catch you in the next video.